Hi everyone, I'm Mihail Stoyan, a master student at TU Munich, and today I'll present the first concurrent implementation of linkages since their creation 40 years ago. This work has been advised by Jana Gicheva and Philip Fett. But what exactly are linkages? They are a data structure for solving the dynamic graph problem, where we have a forest and we want to linkages, strategies, and also perform path queries. 40 years ago, Robert Tarajan, in his paper about the improvement of the maximum flow using push reliable, asked himself the question whether it is possible to use a parallel version of linked trees to solve the maximum flow problem. But nobody tried. Even more recent papers, which design parallel versions of other sequential data structures for the dynamic graph problem, they mentioned that the linked trees are not amenable to parallelization. And this is partly because linked trees use inside them splay trees, which are indeed highly non-parallelizable, as even a lookup in a splay tree modifies its content. And now we have it. Now we can solve the maximum flow problem using parallel linked trees. Now 40-year quest is over, at least from a practical perspective, as we still have to do a theoretical analysis. Just to show you the practical side of the novel data structure, this is the achieved speed up over the sequential linked trees. We observe a 10-fold speed up. Of course, for a star tree, where the root is a hotspot, we cannot see an improvement. But before actually telling you the solution, how we can do this, let me first describe the key idea which nobody saw. We don't have to parallelize the splay trees. We only parallelize the logic of the linked trees themselves instead of the auxiliary splay trees. At first, let's see what a linked tree looks like. In the actual forest, we have regular edges and dashed ones. For a node, there is at most one regular edge, which represents the connection to its preferred child. Each operation also uses an expose operation, which transforms the regular edges into dashed ones, and vice versa. The preferred paths are then stored in splay trees. And now, if we have expose 11 and expose 12, for example, it's clear that we can transform the dashed edges for node 11 into regular ones, or in our case 811 from dashed 1 to regular and 810 from regular to dashed 1. We can do that in parallel without interfering with the edge transformation from node 12. So in our case, we simply have to transform 23 into a regular one and 29 to a dashed one, and we can do that in parallel. Only at the root level, we'd have to synchronize both operations. So to decide whether node 2 or node 7 become the preferred child of the root. So you see now that there is indeed room for a parallelization scheme. And normally, when we do expose, we lock each preferred path until the node, and then we unlock these preferred paths once the final preferred path from root to our node has been created. If you paid attention to this explanation, you would notice that I didn't mention anything about splay trees. And indeed, a splay tree only represents a preferred path. So we actually parallelize the logic of the linked tree data structure instead of the logic of the splay trees. But now, how do we lock each preferred path? We cannot simply lock all the nodes in a path, right? That would be too expensive. Instead, we lock a representative of a preferred path, and indeed, we lock the topmost node in one preferred path. In our case, for the path 1 to 9, we only lock 1, and for 312, 3. As locking the topmost node of each preferred path to the split tree is a bit problematic, since the split tree always changes the pointers of the children. We store an additional lock-free parent array, which called the P array, which stores the preferred paths. We use this parent array to lock each preferred path and then operate on the preferred path using the split tree. It occurred to me three weeks ago, after a discussion with one of my colleagues, that one can indeed also perform path queries, such as min cost edge from root to a node, and also the operation of subtracting value x from all the edges from root to node. And these are exactly the operations we have to support in maximum flow. So a 4-year-old quest is now over that we can solve the maximum flow problem using parallel linkages. For future work, we plan to extend a set of operations with binary ones, such as lowest common ancestor. For now, it seems a bit cumbersome, but we have some ideas and we want to try them out. Moreover, during this project, I realized that there is sometimes a lot of effort to design concurrent data structures. For this reason, I aim at making this process a bit automatic by designing learn concurrent data structures. And what does that mean? You have the source code of the sequential data structure, and you want to get back the source code for the concurrent counterpart. And the idea is simply to do this into an automatic process using machine learning tools. These were concurrent linkage trees, and I'm happy to answer any questions that you might have.